More importantly here, you have to understand the processes. So let's do this again. Let's talk about this gas. Let's do the gas one here again, PV. Now I kind of reverse my colors here. TH, TC, and let's just do this in red here. Let's make this very wild here. You have to know that if you go this direction, that's what the cycle looks like. And it doesn't matter if I start here at 1, or if I start here at 1, or if I start here at 1, or if I start here at 1. I can start any one of those states can be state 1. Okay? Any one of them. And you should be able to, on this diagram, be able to tell me isothermal, there's 2 of those. Adiabatic, there's 2 of those. You should be able to say expansion because you should be able to look at this and say expansion. You should know that all of them are reversible. So you should be, if I put these in a different order, if I put them in, not even if I letter them instead of number them, you should be able to give me where we are and what the next following 4 processes are. You need to be able to tell me that. That is important. Okay, now, if we look at this, what we can understand through this is that, let me draw this again, draw this many times. When we go from 1 to 2, to 3, if you look at that, 1 to 2 to 3, this area under this curve, this is going to be the work generated. Okay, that's going to be the work generated. And then as we go, and I should draw this as PV, we go here TH in our TC, and we go from 3 to 4 to 1, and let's make this a different color, green. This is the work required. This is work generated, positive. The green is the work required, negative. Okay? And so if you put those here on the same graph, so let's do this now, try to put it on the same here, P, V, temperature hot, temperature cold. You have this green here that we drew. And you have this red here. What we're enclosing is going to be all this area inside of here, and this is going to be the net work. The net work is going to be what's enclosed inside of that. The generated minus the required. Okay? So you again need to look at this visually and understand what it means. Okay? I'm going to draw this diagram again. PV. What I often like to do here, when I draw my diagrams, again, I like to draw these lines here to make sure I've gotten my points, and I've made sure there's some area under that curve of those isothermal curves, or sorry, adiabatic curves. What I like to do to myself is I like to pretend that this is like that cycle, and I like to put these over here. I like to make this as adiabatic by putting, how we normally show adiabatic, that insulation. Okay? And I like to say that comes in the top here, this is Q in. And coming out the bottom is going to be Q out. Okay? Does this remind you a little bit of this, what we drew before, this cycle? That we have our TH and our TC, and we have our Q in, and we have our Q out? I think it does. And so the one thing we need to know is a power cycle. We're going to go around this direction. We're going around that direction, and this is going to be our network inside of here. Okay? Isothermal. This is isothermal. The two sides are going to be adiabatic. Okay? Now, what do you know about this? If we go clockwise, we have a power cycle. Well, if we go counterclockwise, if we were to reverse this and go counterclockwise, we have a refrigeration or a heat pump. Okay, you're going to have a refrigeration or heat pump if you go counterclockwise. And you could go up here to how we talked about work in, work generated, and work required, and you would see this would flip. And the work generated would now be the small portion, and the work required would be the big portion. And I encourage you to do that, to kind of take that and show yourself that you are going to need more work is going to be required for those if we do this in a counterclockwise way. Okay? Counterclockwise way. So know this thing, that clockwise is a power cycle, counterclockwise is a refrigeration or heat pump. It always has been the case. We haven't directly told you that, but now we do. Another thing I want to tell you is if we were to go here to this, our PV diagram again, I think this is going to be the last time I'm going to draw it here, TH and TC. Remember how we said state 1, state 2, state 3, why do we have to reject heat? Why do we have to reject heat? If my purpose is to get back up here to temperature hot, why do I have to dump heat, waste heat out? Why can't I just go right back up and go back to where I was? Well, look what happens. If you go from 1 to 2, and then you go from 2 to 3, and you say, I don't want to dump heat. I want to go back to 2. What happens is now you go, and you go right back up here, back up to 2, and then back to 1. What happens there? How much work is created? There's no area inside of that. You don't create any work. So another way to show you that you must have waste heat to create work. Okay, that is an important thing. We have to waste heat to create work. Alrighty. These are important ideas that we need to understand about the Carnot cycle. Your problems that you're going to have for the Carnot cycle are going to be very similar to the second chapter 2 problems, where you're going to have to say you have now 4 processes. Delta U12 is equal to Q12 minus W12. Delta U23 is equal to Q23 minus W23. Delta U31 is equal to Q31 minus W31. Delta U, sorry, not 3-1, 3-4, 3-4, and delta U41 is equal to Q41 minus W41. Okay. Now we know we can eliminate some of these things because some things are adiabatic and some things are isothermal. So the adiabatic Q's we can get rid of. If we're dealing with gases, we know that we can get rid of certain delta U's. We know that when we add all this together, that this is going to be equal to 0, and this is going to be the summation of the heat transfer is minus the summation of the work, and we know that the summation of the heat transfer equals the summation of the work. All of that stuff that we talked about before is still valid, on these problems. So I encourage you, when you're doing these problems, to go back and kind of make yourself a nice organizing chart and help you figure out what's going on. The other thing that we can say here, and that we have new, is we now can say that QH over QC is equal to TH all over TC. And sometimes in our problems we get stuck and we say, I don't know how to find QH, or I don't know how to find QC. I can't do it in my equations, because look at this. This Q12 in my diagram here, this is going to be QH. This Q23 is going to go away. Q41 is going to go away. Q34 is going to be QC. Okay? I may not be able to solve for one of these things, one of these items, so I can go back to this relationship and find out what, if I know the temperatures, the ratio of the temperatures, I can find out what the ratio of the heat transfers are, and if I solve for one of them, I can find out the other. So that's another tool that I have available to me. I have the efficiency tool that I can work with. Okay, so now we're adding tools to your toolbox to solve these problems. Now note, I can only use this. I can only use this equation here. I can only use this equation here if I'm dealing with a reversible cycle. And as we know, as I've talked about many times, the Carnot cycle is a reversible cycle. Okay, so remember that as you're solving problems for your